Okay, good morning, everybody. Welcome back for a fourth day of what I think is going to be more exciting science. My name is Gregory Fiden. I'm at the University of North Georgia, and I will be chairing this session. But without further ado, I would like to turn it over to Rachel Osten from Space Telescope Science Institute and Johns Hopkins, who will be telling us about space weather environments around other stars. So, please.
All right. Thank you. Can everyone hear me? Yeah? All right. Sounds like I'm projecting. So I was very honored to be asked to talk to you at this meeting, and so I'd like to thank the organizers for giving me that privilege. I'm going to be talking about the space weather environment that stars create with some collaborators. Most notably, a lot of the work that I'm going to be presenting here today is the work of my former PhD student. Another collaborator, and a cautionary tale for what happens when you decide to chair the SOC for a very large conference such as this. And I thought I would start at the beginning, or very close to the beginning, as close as I could get to with a quick library search. This is the proceedings of what is now colloquially referred to as Cool Stars 1.5, the Bonas meeting. And I was very heartened when I looked at the introduction to see that there are themes that we're talking about now that I'm going to highlight in this talk were already present then, noting that there are similarities between the kinds of things we're seeing on stars and what we can study in the solar realm, and that the utility of having solar physicists and stellar astronomers get together and talk to each other is that there's quite a helpful relationship between those two fields. And then, as now, there is a difference in how we observe the sun and how we can observe stars. We observe the sun in incredible detail. We have a wealth of space-based and ground-based observatories that we can observe the sun with. We have mostly different observatories that we observe stars with, and we can make up for the lack of detail in studying the stars with just the sheer number. And I give it as an example here some flare observations on over 4,000 stars observed with Kepler, compared with very detailed observations of flares on one star. Okay. Now, something that I want to make sure people in the audience recognize is that when we talk about flares and CMEs and space weather, it's important to realize that these are part of the same phenomenon, something called solar eruptive events. This is a experience in the solar community realizing that these are all parts of the same basic phenomenon. So you see a solar flare over here. This is a nice movie in very high spatial resolution and time resolution. You can see these coronal loops moving around, reconnecting. You've got magnetic reconnection happening high in the atmosphere of the star. That results in the liberation of energy that shows up in particle acceleration, plasma heating, shocks, mass motions. But that's only one part of what's happening. This is the same event, and this is a coronal mass ejection that you can see in the upper right corner. This is the mass that's been expelled from the corona, and the fuzz that you see in the detector are the associated energetic particles. These have energies of anywhere from tens of mega electron volts up to giga electron volts for the particles that actually reach the ground. So those are all parts of this eruptive events. Now we're in the age of exoplanets. This is a workshop devoted to studying the stars, and so I'll just point out that in these press releases on exoplanet discoveries, there's the star nice and central. And there's been a very fortuitous intersection of stellar astronomy and exoplanet science. So I would consider there to be three main parts to exoplanet science, and stellar astronomy is fundamentally in the intersections of all of those. The first is finding the exoplanets, and we've heard already at this meeting how getting better constraints on the fundamental properties of cool stars enables you to do your exoplanet science better. Once you've found the exoplanets, you want to characterize them. Again, you need to understand the stellar atmosphere so that you can maybe remove it. And then finally, you need to understand the environment in which those planets exist. And so understanding stars, I would posit, is an essential component of making progress in trying to answer the question, are we alone? And that's something that the public has a big interest in us addressing in the next several decades. That's something that astronomers have a big interest in trying to find the answers to. And stellar astronomy is a big component of that. One specific topic is exospace weather and exoplanet habitability. So space weather with the knob turned up is habitability. And that depends on stellar magnetic fields, and it depends on stellar eruptive events. This is from the cover of Science, showing the impact of an interplanetary coronal mass ejection on Mars for stars that may be producing coronal mass ejections. Those CMEs will compress the atmosphere of the planet and compress the magnetosphere of the planet and expose the atmosphere to the ionizing radiation. This is thought to be potentially important in the case of M dwarfs. This star's magnetic field creates this ecosystem that can help to set the environment that planets and life experience. One important point that I'm going to want to drive home in this talk is it's the non-flare related components of these eruptive events that have the most impact in terms of exospace weather and habitability, and those are exactly the things that we have very few observational constraints on in the stellar regime. So as another example, this is an astrobiology paper that came out recently looking at the impact of flares from an M dwarf on an Earth-like planet in the habitable zone of this M dwarf. If you have just a flare, the electromagnetic component of the eruptive event, there is basically no impact on the ozone column depth during one of these events. However, if you use scaling relations from the sun and use that to extrapolate what the proton signature might be during one of these flares, you can see that for the very largest flares, there's complete destruction of the ozone layer. But these studies make some fundamental assumptions that we can take what we know about the sun and extrapolate it up by several orders of magnitude, and that everything continues to apply. Okay? So this is sort of a blanket statement that observing flares on stars is easy. I don't mean to imply, I've organized many multi-wavelength flare observations, and it's most definitely not easy. But the point that I want to make is that you can see flares in nearly every part of the electromagnetic spectrum, from long wavelength radio observations that give coherent radio bursts, incoherent gyrosynchrotron emission. All parts of the atmosphere of a star are involved in a flare. And given that there are many different physical processes involved in a flare, you see those signatures in different parts of the electromagnetic spectrum. And so it's really the fact that you can put a check mark in the column for the sun. I sort of designed this table so that you could do that. But it's also heartening that when you look across different types of stars, you see those same signatures when you look in these different regions of the electromagnetic spectrum. And so that is telling us that we're seeing the same physical process in these stellar flares that we're observing in solar flares. When it comes to observing CMEs on stars, it's a little harder. This is a list of some of the observational signatures of coronal mass ejections that could be used or have been used. The one at the very top, this Thomson scattering of photospheric photons off coronal electrons, is the workhorse of how solar physicists study coronal mass ejections. And for stars, we're just not in the same league for astronomical coronagraphs. So we have a number of other observational signatures that we have recourse to. In this talk, I want to talk just about two of them. Association with stellar flares and looking for type 2 bursts. And I will just point out that there are some talks following mine and a poster that describe some of these other mechanisms. Okay? So going back to that comments in the introduction of the Bonas meeting, that we try to understand the solar-stellar connection, we want to understand the solar-stellar connection as it applies to flares and CMEs. So we have relationships between solar flares and solar CMEs. We have relationships between solar and stellar flares. And then the question is, what happens on the other side of this rectangle? Just as a cautionary note, I'll put the dates when we first detected flares and when we first were able to use routine observations of solar CMEs as perhaps a cautionary note about when we'll be able to detect and study stellar CMEs routinely. Okay, so looking at the data that we have from the sun, we can establish empirical scalings between solar flares and solar CMEs. And this is work that was pioneered by Alicia Arnio. Looking at these statistical correlations is additional data by Jeremy Drake and his group. Both approaches find a similar relationship between the mass in the solar CME and the mass in the flare, and the energy in the flare. A slightly different approach, looking at the energy in both components, finds roughly equipartition between the energy in the coronal mass ejection and the bolometric radiated energy in the flare. And this holds even when you account for the fact that in one of these small band passes, the GOES band pass, you're only seeing a very small fraction of the total energy in the flare. So what Scott Wolk and I did was to take this equipartition argument and apply that to observed flare frequency distributions. And in order to do this, we had to establish an energy partition for solar flares, for stellar flares. And that was nice. It was very comforting that we got agreement between solar flares and stellar flares. And what this allows you to do is that you can take any wavelength range where you have a flare frequency distribution and where you can relate the amount of energy in the flare appearing in that waveband to the total bolometric waveband, total bolometric energy, and then you can determine what the flare-associated transient mass loss might be. So as an example, this is a nearby M dwarf, EV-LAC. It has had coronal flare frequency distributions in the upper left. The lower right shows an optical flare frequency distributions. If you look at the plots, you can see the axes, you'll note that the energy ranges are different, but when you convert to a bolometric radiated flare energy and determine what this m dot rate is for flare-associated coronal mass ejections, you get very similar answers. So also the fact that these indices are nearly the same tells you that you're seeing the same populations of flares. And also note that this is assuming that every flare has an associated coronal mass ejection. This is inconsistent with work that's been published by Brian Wood that suggests that this star actually has a very weak wind. So we wanted to answer the question, does a high flaring rate give rise to a high rate of coronal mass ejections? That's the assumption that's inherent in a lot of these astrobiological studies. It's the assumption that was inherent in the previous work. And this is motivated by a happy confluence of renewed interest in the kinds of space weather environments that stars might create and new facilities that allow us to potentially be able to answer that question. So I'm going to be telling you about some radio results. And this is using the new generations of low-frequency radio telescopes. Looking for type 2 bursts, I'll explain what those are in the next slide. The advantage of looking for these particular signature is that it originates from coronal mass ejections and not from flares. Remember that I told you flares are very easy to observe across the electromagnetic spectrum. But we want to have a systematic way to probe the existence and the existence of CMEs and their behaviors. So looking for something that originates from the CME itself is a better technique to start with. Okay. So what we expect to see, we expect that when you have a flare, there is a coronal mass ejection. This is a plot of the association rate of solar flares and solar coronal mass ejections. And above a flare energy of a few times 10 to the 31 ergs, nearly all solar flares have a CME associated with them. The fastest of those coronal mass ejections will exceed the local Alfvén speed. When they do that, as they're passing through the atmosphere of the sun, they will produce a shock, an MHD shock, because they're super Alfvénic. That shock is observable as a type 2 burst. And it has a very specific signature. If you write the prescription for how the signal should change with frequency and time, you get a very simple relationship that just depends on the drift rate depends on the frequency, an angle of propagation. H sub n is the density scale height in the atmosphere, which we can constrain using coronal observations. And the only free parameter is the exciter speed, or the speed with which that shock or CME is traveling through the atmosphere. So it has a very specific signature, which you can see in this dynamic spectrum. Time is on the x-axis, frequency is on the y-axis. It's a nice drifting radio burst. So we can predict the shape using our knowledge of the stellar atmospheres. So my student Michael Crosley's work was to use these new generations of radio telescopes and try to do this. So we picked stars with a high flaring rate so that we could test this association. Nearby, so that we have sensitive measurements. We need constraints on coronal temperature and density so that we can do that atmosphere characterization. We want photospheric magnetic field measurements, previous evidence of radio bursts. And the data actually has all been published. The latest paper appeared this week in the Astrophysical Journal. Now, science is not a linear process. I'm sure you're familiar with that. So this was a paper I'm showing now, but it actually came second or third in the sequence of Michael's work. So we have this technique. We want to detect type 2 bursts on stars, and then we want to infer the properties of the CMEs. How well does that work? Right? I said that solar physicists use coronagraphs primarily to study CMEs. So we took some data from solar flares and coronal mass ejections. We pretended the sun is a star. And then we examined how well we could do in inferring some of the properties of the CMEs based on the analysis of just the radio dynamic spectra and the X-ray flares. And so for this sample of very large flares, we actually got velocities good to about 50%, masses to an order of magnitude, kinetic energy is a little less well. Just as an aside, one of the comments from the referee for this paper it's very revealing of the difference between solar physicists and stellar astronomers. He said, well, you've just proved that this method doesn't work. You can't constrain mass to an order of magnitude. And I said, you could constrain the mass of a stellar CME to an order of magnitude. That's fantastic. Okay, so looking at the radio data that we accumulated, this was from our first paper where we had simultaneous radio and optical observations of EQ-PEG. What you're seeing here is the light curve, the optical light curve, showing several flares on the bottom. It's repeated in both panels. These top curves are the dynamic spectra obtained from our low-frequency radio observations. And so time is on the x-axis, frequency is on the y-axis. The left set of panels show the real component of the visibilities. The right panels show the imaginary components of the visibilities. So basically, that's our test. If it's a real signal, it should be real, not imaginary. And we're looking at Stokes I and Stokes V for circular polarization and total intensity, respectively. Now, if you're in the back of the room and you're squinting and you're thinking, oh, I just really can't see anything there. It just looks like it's a fudge of red and blue. Well, rest assured, your eyes are fine. We didn't actually see anything. We saw several moderate flares, but we did not see anything that we could identify as a type 2 burst. We didn't see anything, actually. So Michael continued undaunted with an additional 44 hours of radio-only measurements. And this time, we did see some radio bursts. The panel on the left shows the image in total intensity and circularly polarized intensity. The figure on the right is another one of these dynamic spectra. Total intensity at the top, Stokes V in the middle, and Stokes U at the bottom. There were some polarization calibration issues, and there was some leakage between Stokes V and U. And you can see, indeed, that there is a burst that shows up in the real component of the visibilities and not in the imaginary component. So that's good. We have a burst. However, I told you one of the strengths of looking for this type 2 signature is that it has a specific profile that we can predict based on our knowledge of the stellar atmosphere. And the features of these bursts, namely the bandwidth, the drift rate, the duration, are not really consistent with our expectations. So unfortunately, we did not detect anything that we could interpret as a type 2 burst. So I showed you what we expected to see, and now I'm going to show you what we saw. So we didn't see any type 2 bursts, unfortunately. Why was that? Is it possible that we were unlucky? We don't like to think that luck plays a role in science, but it often does. This is a plot showing the constraints on brightness, temperature, and source size. And since type 2 emission is a coherent radio emission, you can't separate, it's not expressible in terms of electron density or something that we like to think about, but you can constrain it in terms of these two parameters. And so the triangles in the upper right are the areas that we're sensitive to, given our observing sensitivities. These two dashed lines show the results for those two bursts that we did detect. So, if it's possible that these type 2 bursts are occurring, but they're a relatively small source fraction, a source size as a fraction of the stellar area, we wouldn't be able to detect them. My clicker. Okay. So the next question for why we could not have seen any bursts is going back to the assumption that we have to exceed the Alfvén speed in order to have one of these bursts happen. This is our curve for what we expect the Alfvén speed as a function of distance to look like based on that simple modeling of Zeeman Doppler imaging telling us what the photospheric field is, and then the coronal measurements on temperature and density. The shaded regions show the region of the atmosphere above the surface that we're sensitive to based on the frequencies that we're observing. The horizontal lines are the speeds that we would infer for the CME based on a flare-associated CME. And this shaded region is that fudge factor based on the solar flare analysis. Okay. So, but we're left with the question of whether we're seeing flares but no CMEs. This was the longest timescale search, a systematic search for stellar type 2 bursts at low frequencies. No bursts in 64 hours of monitoring. We were expecting a flare rate of 1.2 flares per hour, so 1.2 CMEs per hour. That's a significant number of CMEs to not have observed. We had additional data at even lower frequencies that have no detections. So this is very high risk, high reward science, and showcases the importance of pointing out null results. So we're left with the question whether stars produce eruptive events and whether we can observe the CMEs. I'm not going to dwell on this slide because we have talks following on theory and modeling of prominence formation and eruption, and then this, suppression of CMEs and active stars, and I'll refer you to those talks for more of the details. So additional work that we can do in context of space weather is looking at the nature of accelerated particles and stellar flares. And for this, I'll point you to Adam Kowalski's poster, who talks about this. There's a laundry list of potential CME diagnostics, and so we need to look at some of those other diagnostics as potentially better for systematic searches, and appealing to modelers to help understand when and how breakout might occur on these stars. So in addition to advising my student on the importance of publishing and null results, even as he was getting more and more frustrated about not having seen anything, and as I kept reminding him that even not seeing something is important, I've been doing future science. And I want to tell you about two different projects that are relevant in this respect. Now, future science is great. You can get all the time you want to do your science. There's no TAC process. Instruments behave ideally. It's really great. You just have to be comfortable with it being a little bit virtual. So I want to tell you about the next generation very large array. This is a project that's being put together right now to come forward before the decadal survey. Think of it as filling the entire state of New Mexico with radio dishes. This is going to have 10 times the collecting area of the Jansky VLA and ALMA, 10 times the spatial resolution as well. In the context of this talk, these radio observations, particularly at frequencies above 10 gigahertz, will enable us to put very sensitive constraints on the radio emission from ionized stellar winds, both in the context of solar analogs and for basically all of the M dwarfs within 10 parsecs. So if you are interested in hearing more about this, I'll refer you to this NGVLA memo. Another future science project, I'm on the Science and Technology Definition team for the LINX large X-ray mission concept that's under study right now. Think of this as a super Chandra. The combination of increased sensitivity, spectral resolution, and spatial resolution will enable us to make significant constraints in understanding the stellar coronal emission from stars and the associated CMEs and winds. And so just to come back to the beginning, the space weather environment that stars create, it really depends on this coronal mass ejections and energetic particles occurring and their characteristics, which are the least observationally constrained. And so if you scale up from solar relations, this is just a cautionary tale for those of you in the audience who work on habitability papers, that just acknowledge that might not be the situation in reality, and maybe explore some of the impacts of a departure from that. I showed you the first systematic probe for CME signatures, which we've not been able to reveal anything convincing. And so maybe this problem is not so bad for M-dwarf habitability. And I will stop there and take questions.
Thank you very much. Before I open it up to the floor, I would just like to remind everybody, please try and phrase everything as a question if you can, but if you do or would like to make a comment, please try and make it as constructive as possible. So with that, I think we'll take questions for Rachel.
Utah from Kyoto University. You mentioned in the possibility of no detection of CME, you suggest a magnetic configuration. And do you think Zeeman Doppler imaging information is helpful for considering a possibility of CMEs?
I think it's helpful because it gives you some constraints on the large-scale magnetic geometry, but when we see flares and CMEs happening on the sun, they're not happening on the global scale, they're happening on the scale of an active region. So having some constraints on what the more localized magnetic fields might be, and in particular, if there's a way that we can constrain observationally the overlying magnetic fields above active regions, that would be good.
The back corner.
Schematic, HAL. I just had to do that, Rich. No, this is Tom Ayers from Colorado. Can we learn anything about mass loss from M-dwarfs, either steady or episodic, from the apparent spin-down rates that these stars experience?
That's a little out of my wheelhouse, but I'll just go back to this plot this is for the solar analogs. These are some constraints from the rotational evolutionary models of Johnstone et al. And so you can see that they're suggesting that there are higher mass loss rates than what we can constrain from these indirect astrospheric methods. That is a little out of my wheelhouse, so I don't want to say any more, and we can discuss that over the coffee.
Joachim Sauer, University of Cologne. You said when the velocity is larger than the event velocity, then you get a shock. Mm-hmm. But it's the velocity with respect to an obstacle. What obstacle is it that you have in mind where the velocity needs to be larger than the faint velocity? It's not the absolute velocity, it's the velocity with respect to an obstacle. So which one do you have in mind?
It's with respect to the surface. I mean, these Alfvén curves are, I know that I've seen plots of the Alfvén speed as a function of distance on the sun, and it varies depending on whether you're above an active region or not.
Katie Hussein, ESO. So we detect in time series Obama profiles, we detect these fast-moving H-alpha absorption transients. Very occasionally, we see them blue shifted, and it looks like they're being ejected. it's our interpretation that they're being ejected. However, we don't know. My question is, what other observational characteristics could we look for when we see those things that might indicate that it really is a CME rather than something else that's going on?
So it would be nice if you could, if there were something that you could interpret as a flare happening at the same time, that would tell you that it was some kind of magnetic reconnection event, as opposed to some kind of prominence formation, an eruption event.
Hello, sorry. One quick follow-up. We don't always see, because we also would detect flares in that, so we don't usually see flares directly associated with those. But would it help to have multi-wavelength observations then for that?
Multi-wavelength observations would be wonderful, yeah.
Jeff Linsky, University of Colorado. We see gyrosynchrotron emission from these stars. It's correlated with flares, and the high-energy particles, the MEV particles, are extended many radii above the star, as best we can tell. So couldn't this continuous creation of high-energy particles, as opposed to discrete events, CMEs, cause a big problem for habitability?
Yeah, so when we look at the gyrosynchrotron emission, we're looking at things that are fairly close to the surface of the star, right? And in the context of the energetic particles, the outward-directed energetic particles, I didn't have time to go into a lot of detail. Those could be potentially a different population. It could be protons instead of electrons. We think we're seeing electrons near the surface in the gyrosynchrotron radiation.
We have time for, I think, one more question over here. Yes.
Sophia Moshu, Harvard-Smithsonian Center for Astrophysics. Good morning, Rachel. I enjoyed your talk a lot. I have an ignorant question. If you can go back to the plot where you were showing the constraints here. Yeah. You passed it.
The future science.
Yeah.
Okay.
Do you know what emission will be from NGVLA? What kind of radio emission would that be?
So this is Bremsstrahlung emission from an ionized stellar wind.
What kind of emission?
Bremsstrahlung.
Okay. Thank you.
If you have additional questions, I'm sure you can find Rachel during the coffee break, but otherwise, let's thank her again.